So let's take a look here. Okay. Now again, I know that math isn't maybe the most interesting thing to you, but it can be more interesting the more you try to engage with it. And if you don't even give it a chance, then, well, I guess you're kind of stuck. So anyway, we have a shape here, right? It says in this situation that your mom has decided to design a triangular garden with the dimensions shown below, with x plus 1 representing the base. Okay, so there's the base of the garden, and then this is like the length of it, of course. Okay, so this is like an aerial view, right? Looking like top down. Okay, so this is the width and the length there, kind of thing. Okay, and we want to determine the area of the garden in terms of x, and then we'll simplify our answer. Okay, so show or explain your work. We're just going to show our work, right? So what is the area of this garden? Well, it's a triangle, right? So what is the area of a triangle? Okay. Well, I didn't teach any of you guys geometry, so at least I don't feel bad about this. But that's okay. All right. Maybe we should get out formula sheets here too. Yes, Tyler, go up. Yes, okay, or in other words, like 1/2 base times height. Okay, there is triangle area formulas here, but yes, triangle area 1/2 base times height. A plus b squared equals c squared is not for area.
That's the Pythagorean
theorem, and you use that to find lengths. You have multiple lengths. Oh yeah, that's right.
I was trying to remember.
And that's fine. I'll just collect it when you're done with it there. And it's no problem that you had it out. And mostly I collect them because I find that students write additional notes on their formula sheet, so I let them keep it. And then that's not what I want for the test. Yeah. If you want to sharpen it too, you can sharpen it back. It's a little temperamental though, so let me know if you have trouble with it. Okay.
I don't think that was what caused it.
Back to what we were talking about here. So yes, the area of a triangle is 1/2 times the base times the height, or base times height divided by 2, like Tyler said. Avery and Christian, you guys are going to have to move if you guys can't pay attention also. It's all Avery.
It was all.
I know. Well, I care about both of you guys learning this stuff, so that's why
I appreciate that.
Okay. All right. So, what is the base of this triangle? X plus 1, right? So then when I go to the area formula here, it's going to be A equals 1/2 times x plus 1, and then what's the height of this triangle? 2x plus 3, yeah. So all we're doing is just writing that out, okay? We're filling in the pieces. Now, I know it's a little bit weird because normally we just have numbers that we're plugging in there. And we simplify the numbers. But this is absolutely, possible, right? X plus 1 is technically a number, right? X is a number, plus 1 would still be a number. 2 times x plus 3 would still be a number. We just don't know what that x is. That makes it more complicated. Okay. Now it says also to simplify. What do you think that means in this case? What do you think we are supposed to do here? Yeah, distribute. Multiply it out. We got to multiply this stuff out. Okay. I'm going to hold off on the 1/2. So I'm going to instead multiply these two things together first. The x plus 1 times the 2x plus 3. So I'll leave the 1/2 out still. Let's go ahead and multiply this out. So this x, what will it multiply with when I go to multiply over here? What does the x multiply with over here? The 2x and the 3 as well. Okay, just like that. So x times 2x, it's going to be 2x squared. X times 3, 3x. Okay. And then the 1, what's that multiply with? The 2x and the 3. Okay, exactly. So 2x plus 3, like that. And then close parentheses there. Okay. And then let's combine our like terms here. So what are our like terms here? 2x. Okay, so the 2x squared and the 3x, are those like? The 2x and the 3x, there we go. Yeah, these are like right here. So, and you can just recycle those.
The first three didn't have names.
Oh, okay. Don't recycle those. Yeah, well, okay. So that's 2x plus 3x is 5x plus 3. And then the last step, we should go ahead and just multiply everything by 1/2. Okay? So half of 2, 1. Okay, you just put x squared there if we want to. What's half of 5? 2.5. That's fine to put it that way. Okay, and then half of 3? 1.5. Yeah. And again, this is something you can do with your graphing calculators too, as far as like multiplying out the 1/2. Now I do want to say this. I see some students, and I really love that they're like, trying to be figuring stuff out and trying to use a graphing calculator to its full capability. But what your calculator will not be able to do for you, okay, is if you type in like 1/2, you can use the X button here on your home screen, right? So you can type in 1/2 parenthesis x plus 1 close parenthesis 2x plus 3, okay? But before you get excited and be like, Mr. Wade, like you tell me this whole thing will multiply out my graphing calculator. If I hit enter, you see I get like a number, okay? And that's because when we use x on our home screen, our graphing calculator does not treat the x like it's the variable x. There's some value stored in for x in our graphing calculator. Either I put it in there from a previous calculation I did, or there's something that a previous user put in, okay? Like maybe someone that owned your calculator before you, okay? If your calculator is brand new, I don't know what is maybe in for x right now, okay? But like right now I can tell you, if I press the x button and just hit enter, it's got this number stored in for x right now, for whatever reason, okay? So you can't, unfortunately, have it do this multiplication for you. You have to be able to do this stuff, okay? So just be aware of that, okay? But I have had students try to do that. Like, that's a great idea, but unfortunately it doesn't work like that. Anyway. As moms tend to do, she has changed her mind and wants to decrease the height by 9 while doubling the base of the triangular garden. What are the new height and new base? Okay? So, it's kind of weird grammar there. What is the new height and base? Probably is what it should be. Anyway. Okay, so let's do new height. Okay, so what are we going to do to the new height? Decrease the height by 9. So how can I represent that? If I want to decrease the height by 9, what should I write here for the new height? So what's the old height? 2x plus 3, and I want to decrease that by 9. So what should I do? Decrease means what operation? Subtract. So we're going to subtract 9. Okay? So it's the old height minus 9. And so let's just combine like terms here. We'll have 2x. 3 minus 9 is negative 6. So there's our new height. Okay? Let's do our new base. Okay, what's our old base? X plus 1. And what are we supposed to do to find the new base?
Square.
Yeah, does it say square it? What does it say to do? Double. What does it mean to double something? Multiply by 2. Yeah, multiply by 2. Not times it by itself. That would be squaring it. Doubling, when you double, you add something to itself. Right? That would be like something to itself. Adding it to itself is doubling, or in other words, times. Okay. So then, how should I simplify this? What should I do here to simplify this? Distribute, yeah. 2 times x, 2 times 1. So 2x plus 2. And there is your new base. Okay? All right, letter C. Determine the area of this second garden in terms of x. Simplify your answers, show or explain your work. Okay, so we're supposed to now find the area of this new garden with the new height and new base. So what's the shape of this garden still going to be? A triangle, right? So we're still going to use our old area formula there, 1/2 times the base times the height, except now when I go to type this in here, what's our new base? What's the new garden's base, the second garden's base? 2x plus 2, and then, and what's the new garden's height? 2x minus 6. Okay, just like that, right. Okay. So again, I'm going to hold off on multiplying by the 1/2. I'll go ahead and multiply the base and height together, and then I'll distribute that 1/2. So I'll leave the 1/2 out. Okay, and again, we're going to multiply just like we did before. This 2x here, what will that multiply with? The 2x and the minus 6. So it'll be 2x times 2x. I'll draw a little arch there. And 2x times the minus 6. So we get 4x squared. And then 2x times minus 6 is minus 12x. Okay? And then this little 2 here, what does that multiply with? 2x and the negative 6. That's right. Okay, so plus 4x minus 12. Okay? Combine like terms. So minus 8x and then minus 12 and then 2x squared minus 4x minus 6. When you take 1/2 of each one of these terms here, this is what our final area is. Okay, questions up to this point? All right, let's look at letter D then, the last one. And they didn't leave us much space for this problem. But anyway, for what value or values, right, so that parentheses around the S means it could just be 1 or it could be more than 1, right? Value or values of X, will the area of the two gardens be the same? Show or explain your work. So if we want to know the values of X for when these gardens will be the same, the two gardens, the first garden and the second garden, we want to know what values of X will they be the same. How should we set that up? How should we relate those gardens? They want to be the same. So what should I write to kind of show that mathematically here? Yes, exactly right, Lindsay. Take the areas and set them equal. So the old garden, the first garden, x squared plus 2.5x plus 1.5 is the same, right, or equal to the 2x squared minus 4x minus 6. We need to solve this equation. Okay? You're like, Mr. Wade, really? 2 quadratics? Well, we can do this. Okay, we actually can. First of all, we have a graphing calculator available to us, right? And I told you guys that anytime you have a graphing calculator available to you and you are trying to solve, bless you, you're trying to solve an equation, how can you solve any equation using a graphing calculator? Remember what I said? We could graph the left-hand side, graph the right-hand side, and look for what? When they intersect. Exactly right. So that's option 1. Okay, you could graph the left-hand side, graph the right-hand side, find the point of intersection. Okay, so let's just do that. I'll show that one to you first. Okay, make sure you type this in correctly. So it's x squared plus 2.5x plus 1.5, and then 2x squared minus 4x minus 6. Okay, we'll graph it. There's the quadratic, first quadratic. And there's the second quadratic. Okay? And it looks like they only intersect once, but maybe they're going to intersect again up here. So here's something else that you guys need to be kind of comfortable with when it comes to your graphing calculator, okay? We need to be able to adjust our window. Unfortunately, the graphing calculator is not super good about like moving this window around and stuff like that. You guys, you know, you have your smartphones and stuff like that, and like, you know, if it was smartphones, like drag down and you'd be able to see more of the top, right? But unfortunately, that's not how our calculators work. And we can't even like, you can kind of use your arrows to move up and down and left and right, but it's not great. We're going to use our window button here, okay, to see if we intersect again higher up. And the way we're going to adjust our window is if we want to go higher up, what do I need to adjust here? If I want to go further up, I need to adjust my y values. Okay, and specifically I want to adjust my y max. Okay, the y max determines how high my graph goes. So let's try to 20 and see if I can see it from there. Okay, so again, there's one intersection point. Yeah, they're getting kind of closer together. So let's see, I'm going to make it like 50 maybe and see if I can see it where they intersect. So again, there's that first garden for different x values. There's a second garden for different x values. And yep, they're getting closer. So I need to continue going up here until I can see that other point of intersection. Oh, we got it right there, point of intersection. So, and there's one right there. So, Press second trace. And which command are we going to use? Intersect. You got it. Okay. Now, there's 2 points of intersection. If you want to find both of them, you have to do it one at a time. Okay. So for the first one, you're going to move your little cursor close to that point of intersection and hit enter, enter, and then enter one more time. 3 enters. And there you go. -1, 0. So x equals -1 is a solution. Okay. And then second trace, intersect. And I'm going to use my arrow key to move to the right and get close to this point of intersection up here. And hit enter 3 times. 1, 2, 3. And there it is. 7.5 is our x value there. Okay. So there are our 2 solutions. Now, do both of these solutions make sense in the context of our original triangle or our new triangle's dimensions? Like, for example, let's check the first one. Does -1 make sense as an x value for this garden? Sure. Did you try plugging -1 into one of these dimensions and see what you get? For example, for the base here, if I plug -1 in, what dimension do I get? 0. It makes sense to have a garden that's got a width of 0? No, right? That wouldn't be a garden. You wouldn't have any space. So we can throw out that -1 answer if you want to. 7.5, it will work, right? We're going to take 7.5, add 1, we'll double 7.5 and add 3. That would make sense for measurements there. And the same thing will be true here as well. If you plug in 7.5, that will make sense. So really the only answer that makes sense here is the 7.5. That -1 gives us a 0 width for our garden. So if you don't throw it out, that's not the end of the world, but do keep your eye out for that, right? Because we're in a context, because we're in a story here, okay, you want to, think about, be analytical. Like, all right, does this answer make sense in the story? -1 wouldn't for the dimensions. Okay? What if you wanted to try and solve this a different way? What if you're like, Mr. Wood, I appreciate you showing us how to draw a graphic calculator, but can I do this without a graphic calculator? And the answer is yes, you can. I'll just briefly show you. I won't go through the whole process here. But to solve a quadratic equation, okay, we can always use the quadratic formula, right? But to use the quadratic formula, what does your quadratic need to be equal to? What number do you need to be equal to use the quadratic formula? It needs to be equal to 0. So in other words, we got to move all these numbers here over to this one side. So I'm going to subtract x squared from both sides. Subtract the 2.5x from both sides. And subtract the 1.5 from both sides. And you get 0 equals x squared minus 6.5x minus 7.5. Okay? And at this point, you could now use your quadratic formula. A is, well, what's our A value here? 1. B is -6.5. C is -7.5. And so then, you could use the quadratic formula. You get the same exact answers as you did right here. Okay? If you don't believe me, I'll be happy to show that to you later. But I feel like some of you guys are just like, I'll take your word for it, Mr. Witt. All right, which is fine. If you just want to use your graphing calculators, that's okay. Okay? But you could use the quadratic formula. All right? All right. Let's try this next one here, number 22. All right, so number 22, you've got a baton twirler. The baton twirler releases a baton at a height of 5 feet. Okay, this is like Gabby Steve, baby. Okay? Baton twirler releases a baton at a height of 5 feet above the ground with the initial velocity of 30 feet per second. The height of the baton, t, seconds after it's thrown, is given by the function h of t. So this is the height of the baton, t seconds after it's thrown, or h of t is the height of the baton in feet. You're going to graph the function, make sure you label the axes appropriately, and then you're going to answer some questions. Letter B asks how high is the baton after 1.5 seconds, and then C, D, E, and F also ask you some questions there too. So I'll give you another 5 more minutes. All right, give this a try. Use your graphing calculators. Yeah. Okay? See what you can do. Yeah, sure, go ahead. Okay, yeah. So let's go ahead and try number 22 there. All right, give it a chance. Use your graphing calculators. Does anyone, I know, let's see here. You need to borrow one, Chris. Yeah. Right. You got one. Anyone else need to borrow one?
Sure.
You get one, awesome. You need one?
Cool, and I have one.
All right. Excuse me. So go ahead. At least try and get this thing graphed and see. Get some. Figure out what kind of scale you're going to use. Maybe we should try. Maybe I should help you guys establish the scale first. That way we're all kind of uniform with what we're doing. Okay, so I'll give you like 5 minutes here, see what you can get done. Okay, I think if you count by 2s on the x-axis or the y-axis, then you should be okay. Or actually, at least if you count by 1s. I don't think you need to do. I wouldn't do 5s. I would say count by 2s. I'd say count by 2s. 5s is gonna. I mean, it'll work, but I think it'll be easier if we just count by 2s. It'll fit. Okay, so let's count by 2s on the y-axis, and I think we should be able to just count by 1s on the x-axis.
You have to label the x-axis then.
Yeah, so what would the label for these numbers be? So that's what you all need to do. So give me a label for these numbers here on the y-axis, give me a label for these numbers here on the x-axis. Hint, use the problem to help guide you, right? Okay. So go ahead. Use your graphing calculators to help you graph this, right? You have the table in your graphing calculator. Use it to help you. Oh dear, I didn't need to go that far. Oh well. I'm going to make... all right, I just realized how squished together this is going to be. So I'm going to put this, I'm going to make every other block be counting by 1. So 2 blocks is 1, and another 2 blocks is 2, another 2 blocks is 3. And I think that's all we're going to need because this is like way, yeah. Sorry about that, folks. Yeah, we only need to go to 2. Excuse me. Anyway, so go ahead and label there. See what you come up with. Give me like 3 more minutes or so. Try and answer the questions too if you can. Yes.
So I put this in. Is this right? Well, and then.
Yes.
Oh, okay.
Mm-hmm. Yep. Looks good. And then you just plot some of those points using the stuff we got there.
Oh.
Yes. And then once he comes back, then Avery, you can go. Okay. And about 1 more minute here, we'll go over this. let's see what we came up with here. So, we're going to type that into our graphing calculators. So negative 16 makes, again, so make sure you're using the negative and not the minus button there. Negative 16x squared plus 30x plus 5. Okay? When we go to label our axes here, what should we label the x-axis as?
Time.
Time, or t. Time in what units will the time be? Seconds is right. Yes, time in seconds. Okay. What's our y-axis going to be labeled as? Height. Yeah, remember? H of t is like our y value here, so h is for height. And it'll be height in what units? Feet. Okay. Believe it or not here, this is like a legitimate, function that is used to determine the height of a projectile, okay? This negative 16, that is the acceleration due to gravity there, right? So like gravity pulls down on the object, so it's having a negative effect on it here. The 30, okay, that is the initial velocity. That means how much force, with how much, kind of like, not force, I guess, but, the speed that you release it at up into the air, okay? And the plus 5, well, that's your initial height. So this is legitimately how, you would use, you could use this function to kind of model the height of an object that you throw up and then, how it comes back down. Of course, there's other things you have to consider, like drag and stuff like that, too. But, it's a good estimate, at least. Anyway, plotting here, okay, if I go to my table, okay, I can see here that 0, we're at 5, okay? So at time t equals 0, I'm a height of 5, right, which makes sense because that's where we release it from, okay? And then 1, we're at 19. So here's 18, so 19 will be right there, halfway between. Let's see here, at 2, I have a height of exactly 1, and then at 3, well, we're at like negative 49, okay? Now the other thing is here, that's only 3 points, and I want to make sure that this is the highest point before I kind of like draw here. So when I go back to my graph, okay, here's my normal viewing window, right? The normal like negative 10 to 10, negative 10 to 10. You can see I clearly need to go up more, so I'll go to my window and change my y max, and let's make it like 20 instead. Just about high enough there. Let me go up just a little bit higher just to make sure, so I'll go to like 25. So there's the max. I want to make sure that that is where I have it on my calculator. So I'm going to have to go to the maximum command, left, hit enter, go to the right, hit enter, go to the top, hit enter. And you can see here that the max is not quite at 1. It's 0.937, and it's like 19.0625. So, our max is just like a little bit closer here, but that's, again, hard to kind of graph, so I'll just kind of like do my best to kind of estimate there. So anyway, now I can connect the dots. Kind of peak right there, and then come back down like that. Okay. Connecting the dots there. So, first question asks, how high is the baton after? Actually, any questions on the graph? Any questions on the graph right there? All okay. First question asks, how high is the baton after 1.5 seconds? So, what can we do to figure that out? What can we do to figure out how high the baton is after 1.5 seconds? Okay, how can we use our calculator to do it?
You do second trace, I think.
Okay. Second trace.
I think, and then you switch the x for 1.5.
So yeah, if we use the value command here, this is one strategy, and this is a great one, Luke, because I wasn't thinking about showing this one, but this is great if you know that one. Okay, if you use the value command, you can see here that the calculator now gives you an x equals blank, and it's waiting for you to type in an x value. Well, our x's, remember, are our t. So this 1.5, if I just type in 1.5 and hit enter, look at that. It gives you the x value and the matching y value of 14. So 14 feet, okay, is our answer. Okay, easy enough, right? What's another thing we could have done? This 1.5 is a time, right? Look at this. We have our quadratic equation right here. What should I put in for t to find the height? 1.5. Yeah, so in other words, we could have also done h of 1.5, which is equal to negative 16 times 1.5 squared plus 30 times 1.5 plus 5. You could also just do this math, and it would also give you the 14 there too. that's another option. Okay. All right, so sadly we're gonna have to turn the page here, and you're gonna have to we're gonna have to flip back and forth maybe. Maybe not though. We can just go back and have it. Sure. I swear. All right, let's do this. All right, so maximum height of the baton, what we're going to do, we go to the graph, and we want to find the maximum. How do we find the maximum of this graph? How can I use my calculator to find the maximum? What's that?
Trace max.
Yeah, so second trace, and we'll use the maximum command, okay? And then we just go to the left of the maximum, hit enter, go to the right of the maximum, hit enter, and then go towards the top, hit enter one more time, and there's the maximum. It says, what is the maximum height? Round your answer to the nearest hundredth, okay? So which one of these numbers here is representing the height of the baton?
The Y.
The Y. Okay, what is this rounded to the nearest hundredth? Hundredth is how many decimal places? So what would this be rounded to the nearest 2 decimal places? 19.06. Okay, 19.06. Okay. Next question, letter D. How long does it take for the baton to reach its maximum height? Well, we go back to this. There's the maximum height right there, right? It's already at that maximum. How long does it take to get to that maximum height? In other words, what time does it take to get to the maximum height?
It's like about a second.
Yeah, about a second, 0.937, right? It's exactly this quantity right here. So round your answer to the nearest hundred. Oops, it says. Round your answer to the nearest hundred. So that's 2 decimal places. So what should I write then here? What's the nearest hundred? 0.9 what? 4, yeah, seconds. Whoop. All right. If she catches the baton at a height of 6 feet, what time does she catch it? She catches the baton at a height of 6 feet. What time does she catch it? So the height is 6 feet. We want to know when the height is 6 feet. So we have a couple options here. Okay. One thing we can do is to graph y equals 6. Okay, so I'm going to graph 6 on my graphing calculator here. Okay, what that shows us is here is 6 feet, and here's the height of that baton over time. Okay, so where can we see that she is going to catch the baton? Is she going to catch it? Where is she going to catch that baton, or what can we look for where she catches the baton? Where they intersect? Yeah. Okay. Now they intersect in 2 places. Is she going to catch the baton at both of these places? Which one's going to make sense for her to catch the baton? Yeah, because normally the baton goes up, hits the peak, and comes back down, and they catch it, right? Unless they drop it sometimes. Right? So we want to find this point. So second trace, we use the intersect command. Okay. And there it is. Okay, 1.84 seconds. All right, and round to the nearest hundredth. Okay, so okay, another option. Okay, is we could set our height equal to 6. So we could do 6 equals, and then I got to go back to this here. Negative 16t squared plus 30t plus 5. And then you could just solve that equation. Okay, so you could set your height equal to 6, okay, and then solve the equation. last but not least here, it says to state a reasonable domain. Okay, so let's go back to our graph here. Okay. What is a reasonable domain for the function? And here's the key words: in context. So let's take away context. Let's just say, boom, here's our graph. What would the domain of this graph be? Forget about the story, forget about the baton twirler. What would the domain for just this plain old graph, what would the domain for that graph be? What's the farthest left this graph is going to go? Well, it's going to keep going down, and it's going to keep going to the left, down to the left. So what's the farthest left this graph will go? Negative infinity. And what's the farthest right this graph is going to go? Positive. It's going to keep going down, but it's also going to keep going to the right as well. It doesn't look like it, but it does keep going out. It will keep spreading out eventually, okay? But that's not what we're asked, right? We're not asked for just the domain of this graph. We're asking for the domain of the function in context. Does it make sense for us to talk about this graph going to negative infinity? In the story, what's our lowest x value we should really talk about? 0, because that's where we start, okay? So our domain here should start with 0, because it doesn't make sense to talk about negative time. We have not developed a time machine yet, okay? 0. And then what is the farthest, what's the farthest right that would make sense to talk about here? Does it make sense to talk about this time going on to infinity? If we're trying to describe the height of the baton, where does it make sense to kind of stop talking about the height of that baton?
Maximum.
So at the maximum, potentially, right, but the baton is going to keep coming back down too. But where would it make sense to stop talking about the baton? Right here, where it hits the ground, right, or where it's caught. So it kind of depends here. I'm going to say just here if it hits the ground, okay, because we don't know if we're still catching it or not. So we're just going to go to the 0, okay? So second trace, let's find the 0, okay? So there's a 0 command, hit enter. Right, you just go over here, make sure you're to the left of the 0 and hit enter, and go to the right of the 0 and hit enter, and then go back in towards the center there, and there you go. So about 2.03 we'll round it to. Okay. Start of baton throw. Baton hits ground. And you don't need to write that. I'm just saying, that's where it makes sense, right? We would not want to talk about a negative height for the baton, because again, the baton's not going to go underground, right? It's going to hit the ground and stop. Okay? All right. So let me help you get started here with this next one, and then I'll help you get started with these two here, okay? And then we'll stop there, okay? And I'll help you with A and B, and then I'll let you guys do C and D for yourselves, okay? So letter A, and there's a couple strategies we can use here. I'm going to show you a quick one that will work for both A and B, okay? So let me show you that here real quick. So again, we can use your graphing calculators. If you press the stat button, so STAT, right there, it's below delete. And this is typically used when we're trying to do statistics. Okay, but you can actually use the stat button here to help us come up with the equation for this quadratic, because that's what it asks us to do. Okay, we're asked to come up with the equation for this quadratic function and the equation for this quadratic function too. So stat button, hit the edit command, okay, and clear out L1 and L2. And by I mean clear, don't use the delete button, hit clear. Okay? And we'll type in our points here into this table, L1 and L2. So we'll do -2, and then the point 0, and then 0, 12, and then the point 2, 0, like that. Okay, so I typed in my coordinates. -2, 0 in the table, 0, 12 in the table, 2, 0 in the table. And now we're going to press the stat button again and arrow over to calculate. And we're going to go down right here, quad, for quadratic regression. This is going to come up with the equation for us. Okay? And so we'll just hit enter down to calculate here. And voila. There's your A. There's your B. There's your C for ax squared plus bx plus c. Don't worry about the r squared if you have that. All right? So we just have y equals -3x squared plus 0x, or plus 12. Okay. There it is. Oops, for f of x. Let me write that f of x. Okay. And then for letter B, we'll do g of x. And it's the same thing. We'll just fill in the numbers from this table. Okay, so let's see if I can squeeze all that on here. So stat edit. And I'll refresh you guys about this, excuse me, on Monday as well here. Okay, and then, so there's my x's, and then 0.25, 3.25, 4.25, 6.75. Okay, so I typed in my table here, stat, calc, quad reg, enter down to calculate, and there's again. So in this case, line. So we get g of x is, so it's 0x squared, so it's just going to be 2x plus 4.25. It was supposed to be a line. I should have used linear regression. Oh well. All right. So then I'll leave C and D for you guys to finish for homework, okay? Hello? Hi. I'm well. Yes, I can. Yeah. Okay, we'll do. Fine. John, Miss Southern wants to go see you, so if you want to head down there real quick, okay? I'll come around and collect those formula sheets, so feel free to just leave your formula sheets out. Leave your formula sheets out. Let me just quickly show you, though, okay? I'm looking at the review for the test, okay? This review, the yellow review I gave you guys, look. Rectangular garden. Determine the area. Your friends change their mind. They want to double and change things. Find a new area. See where the areas are equal. That's exactly what we just did, right? Here, we don't have a baton twirler. We have a batter hitting a baseball. Okay, same kind of questions. Oh, thank you. And then the last one here, you can see there's a quadratic, there's a table. Find the equation, answer the question. Folks, the review is just like what we just did, and the test will be just like what we just did. You have two different ways to see it. Okay. Thank you. So just finish those C's and D's. Oh, thank you. I appreciate that.